This is Ron, and today we're going to do a little bit about drag force and fluid mechanics. So let's get started here. Don't you dare say this class is a drag. All right, I've got a couple of equations here. I'll walk my way through them. So first of all, let's talk a little bit about what drag force is. It's the force on an object that has a moving fluid going past it. So in this case, we've got wind blowing past a car. Now imagine that the car was in neutral and free to move. That wind would try and push it backwards. Well, in this little drawing here, we've got the front of the car connected to a scale. And so whatever that scale is reading, that's the force that the wind is trying to push the car backwards. All right. So what is the equation for the force? Well, here's the fundamental principle. Here's the equation. The force of drag, Fd, is equal to a drag coefficient times 1/2 times the density of the fluid times the area. We'll talk more about that in a second. Let me get rid of that thing. Times the velocity of the fluid with respect to the vehicle, or with respect to the object. In the case of our non-moving car, if the wind is 60 miles an hour, that velocity would be 60 miles an hour. But if our car was traveling 50 miles an hour into a 60 mile an hour wind, then that velocity would be 110 miles an hour. All right, so that's drag force. What we're going to do now is we need to deconstruct it a little bit, break it down into two different kinds of drag force. The first kind of drag force is due to the difference in pressure between the front of the object and the back of the object. When you have an object like this, it will have, oops, oh, Ron, now I'm losing my place here. Let's just hop back out and grab that again. Get rid of this. Well, that's just not what I'm trying to do. There we go. Okay, whatever. Pressure in the front will be higher than the pressure in the back. And if we remember that our equation for pressure is force divided by area, if we multiply both sides of this equation times area, we'll see that when there is a difference in pressure and there's an area, that will give us a force. We call that force the drag force due to pressure. The pressure drag force. Now, what is its equation? Well, it turns out it's the same equation. There are a couple of little nuances. One is that the drag coefficient is called the pressure drag coefficient. And the other is that the area for pressure drag is the cross-sectional area. It's like, what area would I see if I were standing at the front of the vehicle and looking at it? If I could take the vehicle, cut it in half, flip it over, what might this look like? It would probably look a lot like a rectangle with a couple of tires. That's called the frontal area. And that is the equation for the drag force due to pressure. It's one of two different kinds. The second kind of drag force is due to the fluid flowing past every surface of the vehicle. If you think of the molecules of the fluid touching the side of the vehicle, they want to pull on it. And we call that the skin, because it's the skin of the object, friction. And we also just call it the force of drag due to friction. So two different kinds. One due to the difference in pressure, one due to the molecules going along the skin of the object. In this second equation, we have a different drag coefficient and we use a different area. Now, instead of being the frontal area, it's going to be the complete surface area of the vehicle on both sides, on the top, on the bottom. It would be the surface area. All right, let's jump forward here. And from our textbook, we've got a table of drag coefficients for different kinds of objects. Here's a sphere. The sphere has a drag coefficient of 0.2 if the fluid going over it is turbulent, but if the fluid going over it is laminar, then it's 0.5. Here we have a parachute, and the drag coefficient for a parachute is 1.3. Here we have a hemisphere. If in the hemisphere the fluid is hitting the rounded part, drag coefficient is 0.4. If the fluid is entering the opening of the hemisphere, drag coefficient is 1.2. Here we have some bicyclists. If you're riding upright on your bike, drag coefficient of 1.1. If you're in a racing stance, drag coefficient goes down to 0.9. If you're drafting behind somebody, your drag coefficient drops to 0.5. So you can look this up in the textbook, and it's got the drag coefficient for all sorts of different objects. Now, if I were you, I'd have a question. And my question would be, which drag coefficient is this? Is this the pressure drag coefficient? Oops. Or the friction drag coefficient? And the answer is, it's a combination of both. So when they give you this in a table, they are using one value to account for both drag and both drag due to pressure and drag due to friction. Well, then I'd have another question if I were you. If I'm going to use one drag coefficient in one equation, what area do I use? Because on the last page it said that these were two different areas. They are. But in this model, in these tables, they let us use just one of the areas, even though it's accounting for both, and that area is the frontal area. So you only use the cross-sectional or frontal area when using the drag coefficients from this page. Let's do a little example. I've already got it worked out here, and we'll just talk our way through it. So we've got a wind vane. It's got a hemisphere at the top and a hemisphere at the bottom, and it's going to rotate on a hinge. And the question is, if the wind is coming from the left, will this rotate? We've got a force pushing one of the hemispheres that way and the other hemisphere countering it. But as we just learned, an open hemisphere has more drag than the rounded part of the hemisphere. So the question that we're going to answer is, well, what is the moment causing rotation? Well, the moment will be the force times the distance minus the force times the distance. Let's call this force F1, this force F2. And some other information here, we've got a wind speed of 15 meters per second. We've got the diameters of the vanes. And we've got the density of the fluid, density of air. So let's find F1. F1 is 1/2 CD 1.2 rho A V squared. And you do that math and you get 0.265 newtons. All right, well, what's F2? Well, F2 is going to, the same size vane, the same diameter, the same wind speed, the same area, because the area we're using would be the area of the front. The area is the same. It's just pi r squared, or pi d squared over 4. So the only thing that changes for F1 to F2 is the 1.2 to the 0.4. Everything else stays the same. 0.265 newtons, 0.089 newtons. Now, to find the moment, force times distance minus force times distance. The distance is half, 25 centimeters. F1 times D1 minus F2 times D2. And the moment is 0.022 Newton meters. Have a good day.